Hello everyone, so as a part of short video lecture series on control engineering, let us move on to our next lecture, that is lecture number 7. Today we will be talking about the stability of the systems and Routh-Hurwitz criteria. So let us begin with how do we define the stability of a system. So a system is said to be a stable system when it reaches successfully to a steady state after passing through a transient state. So let's say if I have a system like this where this particular response up to here is known as your transient response, and after a certain point of time I'll get some steady state output. Similarly, in case of damped oscillations also, even though the system is having some damped oscillations, after a certain point of time I'll reach to a steady state where I'll be getting some steady state output. Right. Now if I talk about an unstable system, when the transient response of the system goes on increasing in amplitude even as when the time reaches t to infinity, and we do not get any steady state value, such a system is known as unstable system. So let us look it over here. When the transient response is reaching infinity as time t tends to infinity, over here also you can see the damped oscillations are continuously increasing, and I'm not going to get any steady state output in this case, and such systems are known as unstable systems. Now how do we determine the stability of the system? So the stability basically depends on the location of closed loop poles. Now if I revisit this particular term poles, these are the values for which the transfer function becomes infinite. So basically these are the roots of the characteristic equation of a system. Now if all the closed loop poles or roots of characteristic equation lies on the left hand side of S plane, then what we get is the output response consisting of exponential terms with negative indices. Now as this time t tends to infinity, this exponential terms with negative indices dies out, so we get the steady state terms, that we can get some steady state output. So in short, if I want to determine a stable system, all I need to do is to find out the closed loop poles of the system, and if those closed loop poles lie on the left hand side of the S plane, the system is going to be a stable system. And in any case, if I get some of the poles on the right hand side of the S plane, the system will become unstable. Now the S plane over here basically denotes you the plane with real axis over here and imaginary axis, that is j omega axis over here, right? And if I get some of the poles, non-repeated poles on the imaginary axis, such a system is known as marginally stable system, right? Let's look into it with the help of an example. So if I have a function, if I have a system with transfer function given by this thing, right, this thing you have already seen, we have output by input both being in Laplace domain, being a function of S, right? If I try to give a unit step input to the system and try to find out the response in time domain, right? For unit step input, the Laplace we already know it's 1 by S, so I'll be multiplying 1 by S on that side so as to get the output of the system. Now when I multiply it, what I'll be doing is I'll be finding out the solution with the help of partial fraction. On solving this partial fraction, I'll get some answer which looks something like this. Now if I take the inverse Laplace transformations to obtain the response in time domain, I'll get this solution which consists of two parts. The terms of exponential function with negative indices will indicate your transient response, and some constant value will give you some steady state response. Now with this response, if I substitute time t tends to infinity, this exponential function will turn out to be 0, right? So what I'll get is at time t tends to infinity, I'll be getting some constant which is my steady state value, which shows clearly that the system is going to be a stable system. Now if I look at onto the location of poles, the characteristic equation will be the denominator in this case. So I have two poles for which this value will become 0 and transfer function will become infinite. These two values are -2 and -4. Now if I just plot them on the S plane, that is real plane, real axis and imaginary axis, this being my S axis and this being my j omega axis, right? So both these poles will be on the left hand side, -2 and -4. That's why the poles, when they are on the left hand side of S plane, the system becomes stable, or else they are unstable, right? Now I will define some of the terms like critically and marginally stable system. What do we mean by critically and marginally stable system? So a LTI system is said to be a critically or marginally stable system if for a bounded input its output oscillates with constant frequency and amplitude. Let us look it into this graph, right? So if I have bounded input and output conditions, right, the system is oscillating between some with some boundaries, within some boundaries of the output, right, as the time goes on increasing, right. Such a system is known as critically or marginally stable system, right. For this for such kind of system, if I try to find out the location of poles, that is the roots of characteristic equation, and plot them up on the imaginary axis, they turn out to be on the imaginary axis. That again non-repeated poles, right. So if I get non-repeated poles on the imaginary axis, such a system is known as marginally stable system. Again, there are certain systems which are known as conditionally stable system. LTI system is said to be a conditionally stable system if for a certain condition of a particular parameter the output is bounded one. Now this certain condition and particular parameter will be visiting again. This particular parameter is known as controller gain K, right. And if this condition is violated, the output becomes unbounded and the system becomes unstable, right. So in such cases, the stability of the system depends on the condition of parameter, and that's why it is known as conditionally stable system, right. Now there is one more term about relative stability. How do we determine the relative stability of a system? A system is said to be relatively more stable if the settling time for that system is less than the other system. The settling time, we have talked about the settling time in transient response, the time taken by the system to reach steady state is known as settling time. So if the time is less, time is less, the system becomes more stable. If the settling time is more, the system becomes less stable, right. Again, this settling time is inversely proportional to the real parts of the roots. It is inversely proportional to the real parts of the roots. So you can see over here, if I have two systems with roots P1 and P2, the settling time, if the settling time of P2 is less than that of P1, that means the magnitude of P2 is greater than P1. The larger the magnitude, the less will be the settling time, right. This is how we determine the relative stability. So as we move away from the imaginary axis, the relative stability improves, and as we move closer to the imaginary axis, the stability decreases. The system become more prone to instability. Right. Now we'll move on to Routh-Hurwitz criteria. As of now, we have talked about the stability of the system based upon the location of poles. But as the order of system increases, as we move on to higher order systems, like let's say the third order or fourth order or fifth order system, the determination of poles in such cases becomes a cumbersome process. So using Routh-Hurwitz criteria, we will determine the location of poles of characteristic equation with respect to left half and right half of spline without actually solving the equation. Now we are not going to find out the roots actually, but we will determine the location of poles of the characteristic equation, right. So let's say if I have a transfer function like this, a generalized transfer function, this equation in the denominator is known as our characteristic equation, which will give me the values of poles. So if I use this characteristic equation, like this, I can find out the location of poles using Routh-Hurwitz criteria, right. So okay, if I talk about this method is also known as Routh's array method or Routh-Hurwitz method, right. In this method we will be tabulating the coefficients of characteristic equation in a particular way. This tabulation of coefficient will give us Routh's array. So let us understand how do we get this Routh's array. If I have a general characteristic equation given by this function, right, I can tabulate it in such a way to obtain the Routh's array. Now Routh's array basically consists, in the very first column, it consists of the powers of s. So if I start with highest power of s, I have s raised to power n, then s raised to power n minus 1, n minus 2, n minus 3, and so on up to s raised to power 0. Now once the first column is done, I'll move on to the next columns of first and second row, right. So I'll be filling up this one with the given coefficients of the characteristic equation. So in the second column, first row, I'll be writing down the coefficient of highest power of s, that is a0. Then in the second row, I'll be writing down a1. Then I'll move on to the next column, I'll write down a2, a3. Then again I'll move on to the next column, a4, and in the second row a5, and I will go up to a raised to power n. Right, this is how I have to fill up these coefficients, and then I have to determine the value of b1, b2, b3 and so on. So to determine the value of b1, what I'll be doing is a1 into a2 minus a0 into a3 divided by a1. Right, similarly to find out the value of b2, I'll be doing a1 into a4 minus a0 into a5 divided by a1. Right, similarly for b3, what I'll be doing is a1 into a6 minus a0 into a7 divided by a1. Right, so if I just write down this formula like this, you can see this formula and compare them using the Routh series. Similarly, if I want to find out the value of this row of C, so for C I'll be using the preceding two rows. So over here the C1 will be given as B1 into A3 minus A1 into B2 divided by B1. So you can see B1 into A3 minus A1 into B2 divided by B1. Similarly for C2, I will be multiplying B1 into A5 minus A1 into B3 divided by B1. Right. Similarly for D, what I will be doing is C1 into B2 minus B1 into C2 divided by C1. Right. For D2, what I will be doing is C1 into B3 minus B1 into C3 divided by C1. And similarly, I will be obtaining all the terms of this Routh series. Right. So if I talk about generalized coefficient, this looks a cumbersome process, but let's just try to solve it with the help of an example. Right. So over here, before we move to the example, let us understand that how do we determine the stability of the system. Right. So the Routh-Hurwitz criteria, it declares that the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. So if I talk about this column, I have to look about the sign changes in this particular column to determine the number of poles, right, that are in the right half plane. Right. So number of sign changes is what we have to look for. If all the poles are on the left hand of the S plane, the system is stable, that we have studied. Similarly, we can say if there are no sign changes in the first column of Routh table, right, this is your first column, right, so if there are no sign changes in this first column, the system is said to be stable, right, and this is the condition to become for a system to become stable, that all the terms in the first column of Routh array must have the same sign. And if there are sign changes, the number of sign changes gives you the pole on the right hand of the S plane. Right. So let us look into an example over here. Let's say if I have a system like this, whose coefficients are given like this, so I'll be forming the Routh array. Now, how do we obtain the Routh array? What I'll be doing is, as I told you, I'll be first of all writing down the coefficient of S. So I'll be having S raised to power 4, S cube, S square, S raised to power 1 and S raised to power 0. Right, now I'll be forming the first two rows. For S raised to power 4, I have coefficient 1. Right, then I'll be writing down 2, then I'll be writing down 3, then 4, then 5, and now if there is anything or more apart from this, so I'll be writing down 0. As simple as that. Now to obtain the first term over here, what I'll be doing is 2 into 3. So 2 into 3 is 6 minus 4 into 1, that is 4, divided by 2. So 6 minus 4 divided by 2, I'll get 1 as an answer over here. So this is my 1. Similarly for this term, 2 into 5, that is 10, minus 1 into 0 is 0 divided by 2. So I'll be getting 5 over here. Now since there are no more terms on that side, I don't have to move forward, so this will be again 0. Now if I move on to the next row, I will be finding on the first term, which will be 1 into 4, 4 minus 5 into 10, that is 5 into 2, that is 10, divided by 1. So I will get minus 6 over here. Similarly these two are 0, so 1 into 0 0 minus 0, so I'll get 0 over here. Right. Again for the last row, what I'll be doing is 6 into 5, that is minus 6 into 5, that is 30, minus 0 is 0, and divide by over here I'll be doing it is by minus 6. So minus 6 will get cancelled, I'll get 5 over here. Right. So this is how my Routh array will look like. Now if I try to notice the sign changes over here, it is positive, it is positive. Now here the first sign change occurs. So this is first fold on the right half, and then from positive to negative it is going, and from that again negative to positive it is coming. So this is second sign change. So there are two sign changes, which shows that there are two poles on the right hand side of the S plane. So this is what we have obtained as a Routh array, right? I'm correct, yes. And this shows that there are two sign changes in the first column. That means there are two roots with positive real parts. There are two roots with positive real parts, right? Now let's look into some of the special cases of Routh-Hurwitz criteria. So the first case is when the first element of any rows of Routh array becomes 0. In such cases, the effect is that the new row, since we have to divide the new row with the element or the first element of the preceding row, the new elements of new row will become infinite, and this particular test failed. So in such cases we have to obtain special solutions. The solution first will be to substitute a small positive number eta in place of 0, and then once we complete the array, we'll try to find out the value by taking the limit eta tends to 0. The second solution would be to substitute s equals to 1 by z. Now we will be taking the LCM in such cases, and we'll obtain another characteristic equation in terms of z. Now with this equation in terms of z, we'll be forming Routh's array and solving it to determine the stability of the. Let's look into an example of this special case 1. So if I have a characteristic equation of this transfer function, so and if I form the Routh's array out of this, so I can see the Routh's array will be having s raised to power 5, s raised to power 4, s cube, s square, s raised to power 1, and s raised to power 0. So over here what I'll be having in the coefficient as 1, 2, 3, 6, 5 and 3, right? And if I try to find out the first term over here, it will be 3 into 6 minus 6, that is 0. The second term here becomes 5 into 2, 10 minus 3, so 10 minus 3 is 7, divided by the first element 2. Now since I have the first element becoming 0 over here, so what I'll be doing is I cannot obtain the further elements because they will become infinite. So instead of this 0, I'll be substituting it as a small number, very small number, eta. Now if I try to obtain the Routh's array, assuming this to be eta, I'll get a Routh array like this, right? So at the end what I'll be doing is I'll be substituting this eta equals to 0. Now if I substitute this eta equals to 0 and try to find out the solution of this particular Routh array, I can see that we can find out the number of sign changes over here. So over here it is I assume it to be positive. Now over here this is if I take separate terms, 6 minus 7 by zeta. 7 by zeta again infinity, so anything minus infinity I'll get a negative number. So from positive to negative, there is first sign change. Similarly over here I can say that it is going to be a negative number, and this is positive. So there is first sign change over here and second change. So there are two sign changes in this term, right? Two sign changes, right? So that means there are two poles on the right hand side of the S plane. Similarly, if I try to obtain the second solution, that is substituting s equals to 1 by z, so I'll be having equations like this: 1 over z raised to power 5 plus 2 over z raised to power 4. Right. So what I have done is I have substituted s equals to 1 by z, right, plus 3 over z cube plus 6 over z square plus 5 over z plus 3, this equals to 0. Now if I take the LCM and if I try to arrange them, what I'll be getting is 3 z raised to 5 plus 5 z raised to 4 plus 6 z cube plus 3z square plus 2z plus 1. So I obtained a new characteristic equation, and now again I am forming the Routh-Hurwitz to determine the number of sign changes. So we can use either of the method, either of the solution in this special case, and obtain this solution. Fine. Again, what I have done is I have substituted s equals to 1 by z. Now if I talk about the special case 2, in first case what I had is the first element of any row became 0. Now in the second case, if all the elements of the upper row becomes 0, so we cannot move forward in such cases. So what I'll be doing is we will be determining an auxiliary equation denoted by a of s. So if I have such an equation, a, b, c, d, e, f coefficients, and such an row becomes the elements of this row becomes 0, then we will be obtaining an auxiliary equation by differentiating the elements of the preceding row and their coefficient with s, right? So that we can get the new element. Now again it becomes quite difficult to understand this way. So let us understand it with the help of an example. So if I have an equation like this, and again if I just form the Routh array, if I try to form the Routh array, it will be s raised to power 5, s raised to power 4, s raised to power 3, s square, s raised to power 1, and s raised to power 0. So over here if I write down this coefficient, I'll get 1, 7, 6, 42, 8 and 56. Again I'll just correct it. This is 42. Now if I try to find out this row, it will become 7 into 6, 42 minus 42, 0, 7 into 8, 56 minus 56, 0. So all the terms in the next row are going to become 0. So in such cases what I will be doing is I will be trying to find out the auxiliary equation. So how do we find out auxiliary equation? So instead of this we will be having a new equation out of this. So first of all I'll write down this the equation of the preceding row. So it is s7 s raised to power 4 plus 42 s square. Now why square? Because s cube has gone in the preceding one. So and plus 56 as it is, right? Now this equals to 0. Now over here, to just make this problem it's a simpler one, I'll be taking the 7 common over here. So I'll get s raised to power 4 plus 7, 6 and 8. Now I'll be differentiating this equation in terms with respect to s. So if I differentiate this equation with respect to s, that is dA over ds, and I'll obtain the coefficients of the new term. So it will become 4s cube plus 12s, right? So in the terms of s cube, I'll be writing down 4 s cube, then I have 12s. Again I'll be proceeding with the same method to find out the sign changes. So I'll keep this exercise up to you. Just try to find out the sign changes over here, right? Now let us move on to another problem solution that can be obtained using Routh-Hurwitz criterion, that is the determination of range of k. Now if you remember from previous slide, k is the value, that is the gain of the controller, which helps us to determine the stability of a system, right? So if I have an amplifier with gain k, we can determine the range of k for which the system will be stable. So you can look it over here. I have a function with gain g of s and feedback h of s. So I'll introduce an amplifier k, and the value of this k will help us to determine the range for which the system is going to be stable. So using if I just solve it using block diagram reduction technique, I'll obtain an equation like this. And this is my characteristic equation. Right? So if I just solve this characteristic equation for the value of k, I can determine the range of k for which the system is going to be stable. right? So let us look at with the help of an example. So if I have a controller with a feedback element like this, I can obtain the characteristic equation by multiplying it. So I'll get the characteristic equation in this way. And if I substitute this characteristic equation into the Routh's array, you can see I have 1, 18, 77 and k, right? And this a particular first term 0, 0 and k. So I got two conditions, right? So for the system to become stable, all the elements of this first row should be positive. There should not be any sign change. So if I start with positive, all the elements should be positives. That means this particular term should be greater than 0 and k should be greater than 0. So from here I can get the value of k. The value of k will be equal to, from this it is going to be k should be less than 1386 and k should be greater than 0. So this is the range of k for which the system is stable, right? So we can use Routh-Hurwitz criteria to determine the range of k. Now we'll talk about some of the advantages and disadvantages of Routh criteria. First advantages, we can judge the stability without solving the characteristic equation. Second, it gives us number of root having positive real part, right? You can also calculate the relative stability of the system, and we can find out the range of values of k for system stability. There are some limitations, that it is only valid for real coefficient of characteristic equation. If there are any imaginary coefficient, we cannot use Routh-Hurwitz criterion. Again, it does not provide the exact location of closed loop pole, right? It provides the number of poles only. Second, it does not suggest any method for stabilizing an unstable system, right? And it is applicable only to linear systems. We are not talking about non-linear systems as of now, right? So with this, we'll end up this lecture. If you have any doubts, you can mail me up. Thank you very much.